Superconductivity allows us to manipulate attraction and repulsion, which may lead to overcoming gravity and frictionless travel as shown here. When materials are cooled sufficiently, the reduced kinetic energy of the lattice can significantly change their properties, allowing for no internal electrical resistance and the free drift of electrons called superconduction. The current theory in progress to describe this is the Bardeen-Schrieffer theory, which suggests the electrons can influence the lattice structure, causing a distortion of concentrated positive charge that attracts an equal and opposite paired electron. These stable electron pair states are called Cooper pairs and can move unimpeded in the lattice. The most famous property of superconductors is their ability to apparently float. This is caused because an induced current in the superconductor creates a magnetic field that is equal and opposite to the external field. This magnetic repulsion causes the levitation.
The cold has changed the way the ceramic behaves. It's showing another material miracle that's unique to superconductors. Normally, this ceramic isn't affected at all by a magnet. But when the ceramic is cooled and becomes a superconductor, an external magnetic field makes electrical currents flow within it. These generate their own magnetic field, which repels the external one.
Most metals are type 1 superconductors and see a sudden change in superconductivity. Metallic compounds and alloys do not sharply gain or lose their superconductivity and can act at a much higher temperature, usually cooled by liquid nitrogen of a relatively warmer temperature of -200 degrees Celsius, rather than close to absolute zero at -270 to 275 degrees Celsius. These are called type 2 superconductors. The three lattice structures covered in this course are listed here. Depending on the lattice structure, the unit cell will have a specific atom contribution value attributed to it. This is an example calculation of the atom contribution for a unit cell in a body-centered cubic lattice structure. Lattice structure can be used to determine the atomic radii of elements, unit cell lengths, and density. This is the type of question you can expect on lattice structure. X-ray crystallography is used to determine the distance between two layers, which can then be used to determine distances between atoms and so determine complex structures such as proteins and DNA. The Bragg equation applies when X-rays are at an angle that causes constructive interference. Here is a worked problem in which atomic radii are measured using X-ray crystallography and the Bragg equation.